сделать, вот вопрос. Может быть, может быть.
Камеру или а можете еще камеру туда повернуть? Там где вот надо вот эти. Вроде так, что еще.
А центрально это вот.
Это вот эти, ну вот
Техника, например.
чуть-чуть.
Фантастики. Ну, может быть, отодвинуть еще
Так,
чуть-чуть.
наверное, так вот отодвинуть.
И опустить.
So the first problem, suppose that matrix is degenerate, then in its minimal realization, the dimension of H is strictly greater. It's equal to n minus r, strictly greater than n. Then there will be a subspace of such that its intersection with subspace spanned by roots roots is 0. But
So take orthogonal complement. H tilde is orthogonal complement to
yes.
span of pi chart.
And Compton does not and this new tilde does not lie in content because contents of any elements in H0, contents of any elements with non-zero weight is which has weight 0 is some linear combinations of roots.
So why there is no such sum A and B in whole LL of A that can't commute and give some element from H tilde?
I think we can prove it by induction on the lines because every element is some word on generators E and F. But we can just use computation relations to exclude H in any word. So you can see and use triangle decomposition to say it's only a word in E or in F. And then
Sorry, what is H tilde? It's orthogonal complement.
H tilde, because of this dimension inequality, there will be subspace that's there will be a subspace with positive dimension such that it does not accept the linear the space that is spanned by chorus.
Okay, but this we could find this H tilde even if we replace this n from the right by no. Or no, wait.
So if R is less than n, then we can find such thing. Yeah. If it's n, then we can.
R is strictly less than n because it's degenerate. So it's analogous to how we computed V1, V2, etc. It has some weight, which is sum of alpha i's with indices that are indices of i's in this index of is in this word. We want to we only can get element in H with by commuting it with some combinations of F.
Well, we can get an element of H. Like if we commute EI and FI, we get an element of H, HI.
Yes, but it's not in HT.
Yeah, but
You want
so
so that it will lie there.
Why there is no such is some element of n minus commute with element of n plus and get something from HT?
We just compute and get every time such that we move F here, the how to say it. What will be left is some linear combination of roots from P of co-roots. Because we just use relations, we can rewrite this element as by using Jacobi identity as linear combinations of elements of this form that we commute with some f's. This word on the left, which made up of is some indices. Then we also use Jacobi identity with this. We interchange EIs. Here it will be a linear combination. By the Jacobi identity, it will be a linear combination of this two F and E are interchanged. And also there will be a commutator of E and F. If the indices do not coincide, this will be 0. It's not if will be HI, and in this case that will be weight of this word computed on HI. So we interchange Fi further, and we get some here, and we get 0 or HI. So what we will get is always a linear combination of generated HI co-roots from this span.
So you're proving by induction.
Just induction on the length of words.
Like so
you just
right? In
yes. it must lie in H, so it has even length. And I just iteratively use Jacobi identity to move S to the right side.
Okay, and so you say that it lies, so
It will be some linear combination of HIs.
by check, right? Okay,
Yes.
by induction of length of this works. Okay. Two people satisfied? Okay. So this we in such a way we proved one
That it is if A is degenerate, so commutator will be proper ideal.
Okay. But the other way should be more easy, right?
Сейчас. Это работает для это с волной? Кажется, мы... То есть даже для вот Ля с волной доказали. Потому что...
Кажется, да.
Триангулируемое вот это вот разложение есть.
Ну, оно рисовано. Ну да, да. And for the non-degenerate, it's sort of obvious. Because of the computation relations. I mean, it's a
all generators belong to LA commutator with LA, right? That's the only thing that you need to do.
But you know that already from the geometric relations for LA. I mean, not linear span, but ideal generated by. I mean, it will be proper to.
More generators in H.
Yeah, but if A is not degenerate,
the
dimension of
it will be equal to n. The rank is equal to n, and dimension of H will be equal to n. Because it's minimal realization, it has dimension to n minus n minus r.
Where did we use non-degeneracy?
Non-degeneracy?
When we say that generated by H into H high.
non-degenerate means that R equals to n.
Degenerate is H is larger than inner span of P.
So if R equals to n, then dimension of H is n.
This is not true in this case.
самый хороший навык.
Ну как,
Оказывается, нет.
как приводимые корневые системы, они не самые простые. Тем не менее, они соответствуют простым алгоритмам.
Ага.
Это то же самое. Ну, на самом деле, там в книге Касса вот эти условия, которые сейчас рассказывают, нам говорят. Оно для всех матриц, не только обобщенных ротановских матриц. Но на самом деле для обобщенных ротановских матриц оно эквивалентно то, что называется неразложимость ротановских матриц. Ну что в нашей алгебре и Касса-Муди, она не прямая сумма Кассы и
Философской точки зрения это будет нормально, что просто как
Let LA be simple. We want to show that determinant of A is non-zero. It follows from the problem 1 because since it is this commutator is an ideal in LA and of course it is non-zero because it contains HIs, hence it is LA. And now let us show the strange condition on AIs. If I draw a matrix A, what does the condition mean on AI? I have, for example, A1, I1, I1, I2, I2, and they are equal to 2. Then here is I1, I, and here is I1. And the condition that I1, I is non-zero is that I can go from this cell to this cell through this. And it is non-zero. And similarly, simply that it is non-zero, this cell.
The multiplication is
Yes, hence the condition for i's, AIs means that I can go from AII to any AGG in such way.
But what if you can go first from here to here and then from here to here? Like this? For example, you have
No, I can go.
this to non-zero and this to non-zero, but this is zero.
No, I can go from every cell where I go is non-zero. And we can reformulate
just a picture. Like you can go down, right? You can go.
or I can go
right
in this,
down. Or you can go even up, I suppose.
and all cells are non-zero. And I can on the set of numbers from 1 to n introduce an equivalence relation generated by such relations. AII is equivalent to AGG if AEG is non-zero. And I want to show that I have only one equivalence class. But if I have two equivalence classes, for example, without losing of greatity, this is an equivalence class. Then I have here something, and here are zeros by definition. because if here is something non-zero, I can two cells are equivalent from here and from here. And then I can consider a Lie algebra spanned by epsilon 1 to E1 to EM, F1 to FM, and some Lie algebra. Yes, some Lie algebra, for example, L3, L prime, and I claim that it is an ideal. Of course, I can conjugate by epsilon 1 and epsilon from 1 to E from 1 to M, Fs and H, but if I conjugate E or F by E or F, another, I will get 0 because F, for example, FL EJ is 0 for J from 1 to M, and L is greater than M. And it is obvious, yes, and HL EJ is I can write it. It is alpha J from HL EJ, and it is a LJ EJ, but this is 0. It is something here. And if I conjugate E by another E, I will get 0. Hence, it is an ideal. But it is an ideal in L tilde A. Yes. And its intersection with H is not equal to H.
Okay, it's interesting. What if you commute EI with EL? Why
It is 0
Why?
by relations. Oh. Yes.
Well, I suppose, I know. You can commute it with any HI, and since that A is not 0, and if any HI acts on it as 0,
Yes.
then this thing will be 0, since it can't be lie in H. It will be, yes, so you can commute it with any HI. With any HI, it will be 0, since HI, I think by Jacobi identity it will be
Yeah, so we really need this relation you say.
I think it's
I think, yes, we can generate ideal by such elements. Yes, and we don't need to check anything. Yes, hence I need really that L prime is intersect with h is not equal to h, and then if I take a quotient by I, the maximal ideal which intersects h by 0, I won't get h, of course. Hence I need to prove this thing. And I claim that this is in order to find a proper ideal here.
But what happens if L prime intersects with H equals to H?
Then, since every ideal which contains H also is equal to this thing. And I claim such thing. I think it follows from relations, because I have, if I commutate, I have the commutator of some e's where there should be one ei where I is from 1 to m. If I commutate e with this thing, I will get sum from h, and then if I commutate e with this thing, I will also get sum from this e's, or 0. Yes.
L larger than m, and then you commute something f with that, and
No, I claim that. I claim.
no, we want it to be ideal.
I claim that.
It is ideal on a stable.
Yes, and. Yes, origin.
Because if we generate it in a subalgebra, this problem will come. It's like what we do with EI, right?
Yes, yes, here any numbers. Yes, and then.
Если мы вычтем из этого h1, то мы получим h2. Что это теперь? Почему мне кажется, вот это все странно? Что мы сейчас
Нет, ну у нас
говорим, что это будет правда.
для SL3 у нас же нет такой картинки. Там вот это важно. Что там 0. Коммутируют вот эти. Это означает, что картинка означает, что HL от E и T это 0 для I меньше равен M и L больше M. Это...
Все равно вот вопрос, то есть, ну, мы как-то получили вот такую фигню.
Нет, вот это утверждается, что это идеал. Что это вот, нет, что вот это, да, идеал.
А почему, если мы это скоммутируем, как-то мы получим?
С кем?
Ну, вот здесь.
Нет, то есть здесь утверждается, что если вот это я скоммутирую, например, с Е каким-то, то я не получу ничего большего.
Вот, что если возьмем что-то такого вида,
Да.
скоммутируем с таким видом и получим что-то из
Нет, с таким не надо коммутировать. Мы коммутируем либо с любым Е, либо с любым Е, либо с любым F, либо с любым... Это же идеал. Либо с любым Е, либо с любым F, либо с любым H.
Я понимаю. Вот у нас какая-то большая такая запись.
Да. Да.
Вот у нас какая-то большая запись коммутатор для этого. Мы их коммутируем.
А зачем их коммутировать? Мы можем...
Ну, мы можем же так сделать.
Можем, да.
Вот, мы получим что-то из H.
Да.
Можем так получить.
Да.
Вот. Почему это не будет что-то большее?
Да, вот я говорю, например, я с H хочу. For example, I would like to commute these things with HJ. Here I can commute using Jacobi's identity. I will commute HJ with EI1, hence I have here EI1, and at last ES. I would like to commute this using Jacobi's identity. I have to commute EI1 with AJ and get some number. Then EI2, and when I go to ES and compute it with AJ, I get 0. Hence, after commuting this thing with HJ, I will not remove ES, and it will be of the such form. And here I use such thing.
So what you're saying is that, okay, let's take all these vectors, compute them with generated form.
Yes.
Right? And then you will not get anything.
Yes, and if I commute with HJ for J less equal than M, then I will get 0 everywhere where EI with I is more than M. Да.
Возьмем F1 и F3, скоммутируем. Вот два элемента, один лежит в n+, другой в n-. Скоммутируем. Мы получим что-то из H. Почему мы не можем выйти из H1, H2? Почему мы не получим H3? Что останавливает нас от такого?
Если скоммутировать. Ну, я могу скоммутировать с F1, а потом с F2. Ну,
Yes, so you would like to do induction.
no, here we can, I think we should prove two statements that add h preserves these three statements, that add h preserves such thing that at e and at f for some. Yes, of course it is enough. Of course, because at of commutator is the commutator of ats. And for this thing it is not very hard, I think, because, for example, let's take hi. Hi multiplies every e by a number. Hence, of course, if I act by hi here, I will get something and use Jacobi's identity. I will get this thing with some coefficient. And also here and here. Here I really don't need such thing. That the matrix is block diagonal. And for ei here, if I act by ei here, I will get either some linear combination of hi's, where I from 1 to m, if I act by ei, yes, but sometimes some number, and it number is 0 if I is more than m, because here there are zeros, and we have such thing. Here I can act on ei, and get the same thing. And if and on the second one, I can act. Here I have.
You get to the first. You get to this first.
Yes, for the first, and then it will be h. So I. For example, for simplicity, I will act by fi here. And I can act on this thing, and if I don't change es, it will be of the form, of the such form. And if I go to such thing, to es, then and I is equal to s, I will get hs here. And then if ek s is of our set, and if ek is equal to s, I will get I will get es with some coefficient, and it will be of the such form. And if ek is not equal to s, I will get 0. If it if in the first case ek is less equals than m, I will get ek with some coefficient, and it can be arbitrary coefficient, and it doesn't matter, because ek is less equal than m, and this element will be of the such form. And if ek is greater than m, I will get 0 because of this. Because here I.
So this arguments, they work for bigger algebra without factoring by this idea as well, right?
Yes.
So but this factoring will need for that direction.
Yeah, what about
No, here we have proved in one direction.
Yes.
Yes. Because when I factor j by I will get, from here we see that it intersects h by something less than h, and after factorizing by I.
But this is proper already, right?
Yes, but it is
if we factorize it, by something, it can be proper. But still.
yes. And if I factorize by I will get a proper ideal because it will not contain OH. And in other direction, I have some ideal in, I have to prove that Li is simple. So I have to prove that there are no proper ideals in LR. And I can lift this ideal to here. Hence I have some ideal in L tilde R, which contains E strictly. And I want to show that J is equal to L tilde R.
Maximal ideal, yeah? This one that we factorize by.
Yes, yes, E is our maximal ideal. And suppose, since it is strictly inclusion, then it intersects H not only by 0, because it doesn't contain in E. And take some H in and of course I need to say also that since Li is simple, we have such thing. Yes, since determinant is non-zero, we know that H is spanned by these things. And of course there exists E such that alpha I from H is non-zero. Because yes, because this is a basis in H star. And what is if I take a commutator, I will get a non-zero vector, hence EI lies in J. Yes, and hence HI lies in J. And then I take any J and find a chain and what we have since this thing lies in J, we know that
you can prove that, say, I2.
yes. Yes, and how can I do it? I know that it is non-zero, hence
Or I1, even I1.
I1, yes, I1 and I, and this thing because it is non-zero. and then it is a non-zero, and hence ei1 lies in J, and hence hi1 lies in J, and so on. And finally I will get that.
From E to H, how do you deduce that? So if E lies in J, then you say.
Because I can commute it with F.
But F lies in J because.
I don't.
Same
No,
resolution
no,
as Q.
no. It is an ideal, so I can commute with everything.
Oh yeah, that's even. So you can if EI lies,
yeah, you commute with
commute
F.
with FI.
Okay.
Oh, so we proved that Hj lies in J4. So H lies in J, and all E's and F's lies in J. Hence J is L tilde A.
Мне интересно. Мне тоже. Как-то она нереалистична.
Okay. So let's. So, first of all, a little question. Did we know that such things is true? That this is automorphism of roots, Weyl group.
Wait. Maybe this?
Oh, yeah, of course. Like that. Did you know this?
Это же группа.
And?
So the question is.
Yeah, we like.
If I take a root, apply this, then this will be a root.
А в чем смысл исправления действительно?
Не, ну.
Получим обратный корень.
Ну в этом плане.
Тут не может быть неравенства.
Неравенство. Да.
Не, ну да, ну как вопрос не в этом все равно. Вот просто вот когда мы доказывали это для, для полупростых обычных алгебр, мы доказывали это с помощью SL2 под представление. А здесь мы просто типа говорим, что это подгруппа, порожденная сытыми.
Там SL2 нету под алгеброй?
Там есть SL2 под алгеброй.
Точно.
Бесконечно мерное представление.
Ну да, там бесконечно мерные, поэтому мы бесконечно мерные в первом семестре не разбирали.
Нет,
Поэтому то, что если там есть лямбда, то есть и минус лямбда, это не факт, по-моему.
Сейчас, мы вообще доказывали, что W от π это какой-то более сильный тип. Нет, то, что вот это вообще.
Но мы еще говорили. Мы говорили то, что W это группа, это автоморфизмы корней, порожденные сытыми. Вот, кажется, как мы говорили, да?
Мы все равно пользуемся тем, что сыто это перевод корня в корень.
Ну да. А сейчас мы вот это знаем или это?
Мы этого не знаем, потому что тогда у нас было конечномерное. G у нас было конечномерное.
Да.
И мы пользовались конечномерностью представлений SL2.
Да, вот в этом и суть. Но вот это я не знаю, как доказать. Вот дальше я могу.
Верно вообще?
А как доказывать? Ну да.
Раньше мы говорили, что у нас есть представление SL2 тройки, а там, ну,
Ну, а в конечномерных представлениях SL2, там если есть лямбда, то есть минус лямбда.
А нельзя ли просто предъявить какой-то
Элемент?
корневой да, вектор, который значит, будет лежать? Я просто беру там корень, да, какой-то альфа.
Ну, то есть, вот смотрите, вот у нас лямбда, альфа было, а стало, то есть, альфа минус альфа, что там, альфа h-ит, альфа ит. И нам нужен какой-то такой корень, да? То есть...
нужно много раз Е применить,
Ну
правильно?
да. Я просто возьму, а у меня любой альфа, это мы знаем как бы из треугольного разбурения, что это вот что-то такое.
Да.
Он на самом деле вот в спэне находится в пиче.
Ну, мы так R все определяли более-менее.
Нет, мы определяли, что это все как бы веса. Вот,
А, да, вы правы.
но мы как бы из треугольного заложения знаем, что они все вот так как-то записываются.
Мгм.
Вот. Ну, и мы возьмем, значит...
А мы знаем, как SI действует на лямбда жит, альфа жит.
Нам
Знаем.
важно понять, что мы не ноль получим, когда мы много раз будем применять все-таки ешку.
Не, а я сейчас не понимаю. Ну вот мы знаем то, что они все так выглядят. Но это правда, что любой альфа, который можно вот так записать, это корень?
Не, вообще-то это должно быть верно, потому что все
Да.
равно там модуль Верман, если 2 получается. Вот.
Окей.
И там, если мы применим как бы...
Ну в модуле Верма это правда, что если у нас есть лямбда, то есть и минус лямбда. Но у нас же не все бесконечные представления, это модуль Верма.
А можно ли вермать неверно?
Что? Если у нас есть лямбда, ну если лямбда больше нуля, вот так вот. Ну да. Не, ну это мы говорили про то, что... Сейчас. То, что вот мы как в этом, в конечномерном случае мы просто под представление SL2 искали. Вот. А здесь типа оно бесконечное, и поэтому непонятно.
Может, вы просто посмотреть, может, у вас нет такого соотношения.
Ну вот к вопросу о рисках.
Ну, это такой вопрос. Нам надо за 3 минуты что-то.
Да.
На самом деле это очень просто. На самом деле дальше.
Ну вот дальше, вот после этого я могу объяснить, если хочется. Ну давайте тогда вот это, видимо, на лекции обсудим или... Окей. Now if we know this, then we know that if we have alpha in imaginary root, then we know that v of alpha is still root. Yeah? That's suppose that it's not imaginary. That means that it's real. That means that v of alpha looks something like we prime alpha I, and that means that alpha looks like something like v minus 1, we prime alpha I. Then that means that alpha is real. Okay, then what we do with if alpha is that's a contradiction, and we say that v of alpha also imaginary root. What if alpha is R plus imaginary? That means that alpha is something like sum of an I alpha I, where an I lies in that plus, that larger than 0. So after this we can say that well, we know that Weyl group is generated by SI, So we want to know that SI of alpha is not. Now we know that it's imaginary. Everything that we know that V of alpha is not lies in R minus. Yeah. We want to prove that for any I, SI alpha is not in R minus, since it's just a Weyl group is generated by SIs. So now let's say, suppose, no, I don't think I said it. Yeah, let's just write something. So SJ, SI of alpha is something like this, is sum of Ni, sum of Ni S, no, that should be Si alpha j. Yes, that's how, since Si is linear, that's we know. So this sum of Nj, where j not equal to I, should be something like alpha j minus it's AJI alpha I plus minus Ni alpha I. That's how it looks like. Yeah. So let's say that sum of j not equal to I alpha j plus, we know that AJI, there we say that AJI, if j not equal to I is less or equal than 0, that means that we can just say that it's modular. This like AJI minus Ni alpha I. That's like that. There should be Nj, and there should be Nj also. So that's true. So now we know that there's only positive or negative root, and it can be something in between. And we know that alpha I, alpha j is linear independent.
Something strange here.
What? Yeah,
Is it big sum?
This sum, this also should be sum. Yeah. This should be sum j not equal to E. Yeah. Yeah, that's all sum. No. Here. Now it's okay, yeah? Cool. So, like that, and since we know that there is only, like, root can be, can't look like with, like, something plus alpha I minus alpha j, since it's only positive or negative. That means that if all this, if there is something, like if exists this I, if exists j that nj not equal to 0, then this also should be positive, since there is only positive roots and negative roots. So then there's a situation if all for all j and j is equal to 0. That means that Si alpha looks like it's minus ny alpha I. Is it true? Yeah, there's everything.
No, the thing is that you always have at least two positive ni's.
Yeah, why?
Because if it's only one, then it's just alpha equals alpha I.
Well, it could be alpha equal ni alpha I with some positive scaling. Yeah, and actually I have a. I don't understand actually.
So,
What?
yeah, so the only way how you can obtain this device is that to apply at EI, how many times? In 5 times.
Yes.
Which is 0, of course.
Uh-huh. Yeah. So that means this situation is also impossible.
Yeah.
So that's all.
Yeah, so actually you are right. This is something I overlooked.
About Weyl group of root.
Yeah, about this. Yeah, it is true actually that these relations, these set relations, they satisfy from L of A. But this we didn't prove this.
And
If we know that this, then we know.
we know that?
Yeah.
How?
Because the action of SL2 on LA, on each SL2 triples is locally important. And then we had this similar problem earlier in semester, which say that then root system is actually symmetric with respect to action.
Okay.
So if you prove that your SL2 triples act locally importantly, then
Okay.
it's true. I cannot say now you can avoid this. Yeah. Yeah, maybe not. Yeah, okay. Yeah, thank you.
У нас получается лекция 20.
Today I would like to tell something about SL2 hat, SL2 affine, and see how come it is a Kac-Moody algebra. All right. Definition. So we define first vector space like this. So this is called affine SL2. Why is it affine? Because it also has translations. You'll see why. So it is SL2 tensor C TT inverse. First is a vector space, and plus two other vectors, C and D. The vector space is such thing. So translation, basically, it's a translation is in the degree of T. So that's a translation that you add, kind of. So Lie bracket is given by the following. So I commute x tensor t to the power I, y tensor t to the power j. Then by definition is just xy, bracket of xy, tensor ti plus j, plus I delta I minus j trace x y c. And then also I should say that C is in the center, so C commutes with everything, C with any A from SL2 hat is 0.
Trace of x, y.
Yes, x and y, they are elements of SL2. So I can consider just a trace form of it.
So it's like killing form.
Yeah, up to multiple killing form. Yeah. So all this has more advanced definitions, but this is some very, concrete example of more advanced constructions that people have. So D, yes. D commutes with C, of course, by 0, and D commutes with X tensor Ti by multiplying by I, X tensor Ti. So D, in a sense, is a degree operator. So this, at least, algebra is graded, and the grade corresponds to the power of T, and C also belongs to the 0 degree. And commuting with D just gives you back the degree of the corresponding homogeneous vector. Yes. So all this construction is known as so this thing is known as a loop algebra. And then you central extend it, so C is in the center. So if you just forget about this part, this is just center extension of loop algebra. And then you also add this one, and in a lot of cases, people just forget actually about this one and just define a finally algebra just like this, the central extension of loop algebra. But to see that this is Kac-Moody algebra, we also need to add this. And this is add D is actually a derivation. And so when we add this, people also say that we adjoin a derivation to the central extension of loop algebra. So this is a quick definition of SL2 hat. Now, if I take a generalized Cartan matrix like this, so this is the end of definition. So now let me take this generalized Cartan matrix. And the theorem is that L of A is exactly SL2 hat. So it's isomorphic as SL2 hat. And so the rest of the time, maybe not. Maybe I would like to say more than this, but let's try to prove this. So we would like to so first I will need some minimal realization of this matrix. So let me first I will have the same notations as we always had. So E, F, and H are standard bases. In SL2, and I would like to consider Gothic H to be a three-dimensional vector space spanned by H and C and D. This is commutative. This is commutative subalgebra of SL2 hat. So when I say if I have an element G of SL2, when I just write G, I think of G tensor T0. Okay, so I also would like to define H1 is just H, so this H, and H0 is C minus H. So we will have, so my matrix is 2 by 2. To define minimal realization, I will need to give you vector space. This is the vector space. I need to give you some linear independent subset of this space. So instead of writing H1 and H2, right, this subset should contain n, in our case, 2 elements, right? So instead of writing H1 and H2, I will have H1 and H0. And H1 will be just usual. What is labeled by 1 is just usual elements of SL2. So the logic is like that. And H0 is something strange. Okay. And then I need to give you, this is pi check. And then I need to give you pi. So I also will have alpha 0 and alpha 1. So I defined alpha 0 and alpha 1 as follows. Alpha I of hi is a ji. So ij is ijth element of this matrix. But this does not fix me an element of H star. I need to give you more conditions on alpha. So I and j here runs from 0 to 1. And also, so I need, so my basis is H, C, and D, or H1, H0, and D. So I also need to give you values of alpha i's on D. So I say that alpha 0 of D is 1, and alpha 1 of D is 0. So the usual root does not see the degree, in a sense, and the other one sees it. Also, this already fixes me alpha 1, alpha 0, but just from these relations, you also can see that alpha 0 of C and alpha 1 of C is 0. Just looking at Cartan matrix, at this condition, and how H1 and H0 are defined. Okay, so I claim that I defined, define minimal realization of A. So H, pi, which is alpha 0, alpha 1, and pi check, which is H0, H1. This is minimal, wrote like this, minimal realization of A. The only thing to check is the dimension of H. It's 3. It should be 2n minus rank A. So it is 2 times 2 minus 1. So 3. And it matches. And we also need H0, H1 to be linearly independent, and alpha 0, alpha 1 also to be linearly independent.
Matches with what?
It matches with dimension of H. So I defined H to be three-dimensional. And this thing also should be 3. So, yes. We checked the question mark. Yes, so H0 and H1, of course, linearly independent. If I did not have this condition, alpha I and alpha 0, alpha 1 would be linearly dependent, but because of this, they're also linearly independent. Yes, okay. Now I need to give you, so I gave you minimal realization, now I need to give you what we can call Chevalier generators. Okay, so as I promised, everything with label 1 is just our normal SL2. So I would like E1 to be E, and I would like F1 to be F. And then I would like E, so I need to give you E0 and F0 also. And this one is pretty strange. So this should be generators, right? And this is a degree 0 thing. So it also generates SL2 for me, right? But also I have powers of T, which are generated by T and T inverse, right? And so E0 should increase power of T, so it should be tensor T, but what stays in here is actually surprising, is F. And here it's E tensor T inverse.
So it's like decrease degree of the left one and increase the right.
So I don't know, it's just some mnemonics, I don't know, you should ask Katz maybe how this works, why. but this, so you can also do it for cell 3 or for any simple G. So your EIs will be just usual F. And this one will correspond to, like you will have this twist, T and T inverse, in the same way. But this E and F will be, will correspond to the longest root. So this is the construction. Well, we'll see. We'll make some computations that will justify such choice.
I wanted to ask, so we said that for any A it has a minimal realization, yeah?
Yes.
But what if it have a lot of minimal realization?
They are isomorphic it's a good question, and they are isomorphic in some natural sense. So there's some linear map that maps like H's to alphas, and which respects alpha I of HJs. Mm-hmm. Okay. Well, it should respect, because like if they both are minimal realizations, then I mean, they are the same. Yeah. Okay. So we need. So let us make a plan now. So we need to check to prove this. The following things. So first of all, that my EI, Fi, and H, they satisfy relations similar that we have in L of A tilde. Then I would like to check that these things generate the whole SL2 hat. And third, I would like to check that in SL2 hat we have no ideals. There is no ideal I such that I intersect H is 0. So I claim if we check these three things, then we prove theorem. So let us see why. Of course, 1 and 2 is very natural to check. So 1 and 2 will mean that we have surjective homomorphism of Lie algebras from L of A tilde to SL2 hat. And then 3 will mean that there is surjective homomorphism. It actually factors through quotient by the ideal. So L of A to SL2 hat. Right? So since yeah, so this ideal will just go to the kernel since there are no such ideals. So image of I will satisfy this property, right? Therefore, it will belong to the kernel. So this map factors through the quotienting by this ideal. But now the question is, what's the kernel? But the kernel is 0 because, well, you have, say, this map phi tilde, and this, let's call it phi. So first of all, I claim that phi tilde kernel of phi tilde restricted to H, the H in LA, is 0. Just because image of H is H, so H in here goes to H in here. And dimension of H in here is 3 or less. And dimension of H is in here is 3.
Why is 3 or less?
Well, because as we discussed with Nikolai, we never know that we don't quotient. Like, I mean, maybe we have some, like in our idea of relations, we have some strange relations that kill some of H's for us. You never know. Like, it's not clear. Maybe you can end up with some proof, but I couldn't, like in a break. Yeah. So, but here we don't need it because H maps to H, and then here we know its dimension is 3, and here it's less than 3. So actually 3 in here as well. So, but when we quotient by ideal, which has trivial intersection with, okay, whatever, just quotienting by any ideal, just gives me the same kernel phi by restricted to H is 0. This means that kernel of phi intersection with H is 0. It's ideal and which intersects trivially with H. So therefore, kernel of phi is just 0 ideal. Otherwise, we can lift it to L tilde of A, and it will intersect non-trivially with H, right? But it will contain I then. But I is a maximal such ideal, which intersects trivially with H. So therefore, kernel of such map is 0. And if we check these 3 conditions, then we check that SL2 hat is exactly Cauchy-Modular algebra corresponding to this generalized Cartan matrix. So you see, this is much easier than try to check that there are no other relations than the third relations. It's not even clear how to approach such thing. Maybe for SL2 you can do this just by brute force, but still, maybe not. I don't know. But like this reasoning actually generalizes to other stuff, and like theorems is much easier to prove if you start with such a definition of Cauchy-Modular algebra. Okay, so let us follow our plan. Okay, I will not check all the relations. I will check only maybe more or less interesting ones. Of course, I can check like E1 with F1, it is H1. Because it's just E with F. What about if I, yes, I erased commutation relations. But okay, we'll recover it. So x tensor t I, y tensor t j is x with y tensor ti plus j plus I delta I minus j trace of x, y, c. So let me check E0 with F0, for example. So this one, so I have F tensor T, E tensor T inverse. So according to my formula here, I should write F with E, right, plus, well, delta I minus j is 1 in this case, right? So 1 and plus negative 1 is 0, right? So therefore, this term is non-zero. I is 1. So I have trace of F, E, C. Right. So this is yes, this is very unfortunate. Yes, so this is just number I. Yes, so here we have, this is 1, right? So C, and this is minus H. So C minus H, and this is exactly H0. So because we switched this, we get this minus H, which we needed. I don't know if it's что подогнали к чему, да? Вот это EF или H0, я не знаю. Да. Ну, или ничего не подгоняли уже как бы там из каких-то высших материй, это все известно. Да. Значит, ну хорошо. Next. So what else? Let us maybe check H0 with, we should have this -2, right, in the matrix. So let's see if it happens. So I have C minus H with E. No, I think this minus is needed because of -2. Then we should switch E and F maybe. With E, right? So this is C with E is 0, and then I have -H with E, so -2E. And this is exactly the -2 which is in the Cartan matrix. And okay, we can check all the relations, but let me just not continue doing this. Yes. Very well. So let's do number 2, item number 2 of our plan. How do I prove that these are generators? So let me denote by M. So let M be the subalgebra generated by what we need. Yes, EI, FI, and H. Как алгебра. Нет,
либо как алгебра, либо как...
нет, утверждение, что они порождают ее как алгебра. Вот. Значит, окей. So we will prove by induction on K such that X that SL2 tensor T to the K belongs to M. Then we are done.
А как они D породят?
D уже в H. И C, да, тоже там.
Да, а у нас induction тут и вверх и вниз, что ли?
Я докажу только для, значит, K больше нуля, а для K меньше нуля я аналогично, да. Окей. Of course, if I take K equals 0, it's obvious, right? So, but I don't want this base because the step that I'm going to do it will not work if I take base like that. So I need a base K equals 1, actually. Okay, base K equals 1. It requires a bit more work. So I define such set. It's all X from SL2 such that X tensor T is inside M. And I would like to see that this is an ideal. Non-zero ideal. So first of all, it is non-zero because F tensor T is, so F tensor T is inside M. Because it is E0. So therefore, F is in E. So therefore, I is not zero. Because M is subalgebra generated by EI, FI, and H. And I is here 0 and 1. Okay, so I would like to see that I is an ideal in SL2. Therefore, I take X from I and Y from SL2. And I consider X, Y. I would like to see that it is in I. So there, it means that I would like to tensor it with T and see that it is in M. But this thing is the same as X tensor T with Y. But X tensor T is inside M. And this is also inside M because it's in SL2. So therefore, this is inside M. So we actually proved that I is an ideal. So it's the whole SL2. So therefore, I is an ideal. So therefore, I is SL2. So therefore, SL2 tensor T is inside M. So K equals 1 proved. Now step of induction. Step of induction even easier. So consider Z tensor T to the power K inside SL2 tensor T to the power K. Okay, SL2 it's simple, so therefore it coincides with its commutant. So Z is X commutator with Y for some or linear combination of those, of course. But I mean, just we can assume that it is a commutator for some X and Y from SL2. Right. Therefore, I can write the following thing: Z to the tensor T to the K is X tensor T to the tensor T, and Y tensor T to the K minus 1. So then by induction assumption, this is, so by base, this is M. This is in M. This is by induction assumption, this is in M. And so therefore, the whole thing is in M. You see, if I had T equals 0, this will not produce me the step. Okay, so we proved number 2 of our plan. That actually IFI and H's, they generate the whole SL2 hat. Now, number 3 of our plan is to prove that there are no ideals that intersect trivially with H. To do that, we just study root decomposition of SL2 hat. Right? Actually, so if I just denote, SL2 hat as G hat, right? I can actually write G hat. It's direct sum of over some elements from H star G hat alpha, where G hat alpha. Well, actually, I don't know this yet. I can just define G hat alpha to be what we always wanted to be. It's just all elements from G hat, right? Such that commutator of H with X gives me alpha of H X. This is for any H from H. So these are root subspaces, and let me find actually all G alphas which are not 0. So actually decomposition of this. Well, we already know that it admits weight decomposition because it's infinite representation on finite dimensional commutative algebra H, subalgebra inside. So by problem on a seminar, we know that it admits weight decomposition already. Yeah, so if you have finite dimensional commutative Lie algebra H and some representation of this algebra, then it admits weight decomposition. Okay, very well. So I would like to introduce some element delta in H star. I just define it by how it acts on basis of H star. So it acts on H1 and on H2. It evaluated at H1 and H2, gives me 0. And when I evaluate it on D, it gives me 1. So it sees D only, degree. So H1 and H2 and D, it is a basis in H. So I defined an element delta in H star. Yes, sorry. H0 should be here. So define this by.
So it's like dual basis, and this delta is dual to D.
Yes, exactly, yes. Then I claim that the following. So if I consider C of E tensor Tk, so it's one-dimensional subspace spent on this vector, then this is G hat alpha plus alpha 1 plus K delta. Then C of F tensor Tk, this is G negative alpha 1, G hat negative alpha 1 plus K delta. And C of H tensor Tk. It's exactly G hat K delta. Okay, so to check this, you just need to use commutation relation. So I just take, say, let me check. So let's check. Say number 1. I can check that this is inside here, right? So how to do this? I take E tensor Tk and commute it with H0, H1, and D, right? So let me commute it with H0 or H1, I don't know. That's yeah. So we can. So computation just says that it's exactly. So what you have is again this vector multiplied by alpha 1 plus K delta of H0 in this case, or of H1 if I commute with H1, or with D if I commute with D. Okay, and so you can similarly check for that this is inside here or this is inside here. But the equality is because what I tried to write, that G hat is actually well, it's a sum of G alphas. Because that means that weight decomposition. So if at least, of course, H is inside G0. So you kind of have all the vectors exhausted. If at least one of these equalities is actually proper, it's not an equality but proper inclusion, then you don't have equality here. So because we have weight decomposition and all these things, they are in the corresponding weight subspace. So if you have a proper inclusion in such of these cases at least, then you don't have enough vectors to have this equality to G hat. That's it. Okay, are we going to check this or not? Okay. The most I guess interesting is to check with D actually, because you have this delta, right? So if you take D with E, this will give you. It's not like so interesting. It's just why do you have this delta, right? You will have K E to tensor TK, right? But this K, I claim, is exactly alpha of D. Alpha, so here I should say alpha 1 plus K delta of D. So alpha 1 of D is 0. And this is, okay. So my, I have actually, I can now write that G hat is like this, where alpha is R is the following set. So now I know the whole all the roots for G hat. It's plus minus alpha 1 plus K delta and L delta. So K here runs over Z and L runs over Z but not 0. Maybe if I add also H here, then R is like that. So this is my roots, what I call roots. But my goal is what? To prove that there are no ideals intersecting trivially with H. Okay, so by contradiction, let us consider such an ideal. Okay, let I be a non-zero ideal of SL2 hat such that I intersect H is 0. So then so SL2 hat is a representation of, or G hat we denoted it as a representation of H admits weight decomposition. And I is a sub-representation. So it also admits weight decomposition then. Right? So I as a representation of H also admits weight decomposition. Okay, so I intersect H is 0, right? So we have some weight vectors in I, what I'm trying to say. And these weight vectors are not of weight 0, because I intersect H is 0. So therefore, we should have so I contains an element of the form X tensor t to the power k, where x is either e or f or h. So these are all weight vectors that we have.
X is some element of a set.
No, it's not a linear combination of those. Linear combination of those would be not a weight vector, but it should be exactly, it's like maybe a linear multiple of it, like a scalar multiple of it, but not sum. Well, of course, if it contains a scalar multiple, it contains this thing itself. So then I would like to take y, another element of SL2, to be according to what x is. If x is e, then I would like to take y to be f. If it's f, then I would like to be at e. If h, then h. So y to be this, respectively. Then I would like to consider the following. So x tensor ti, I would like to commute with y tensor tk, sorry, y tensor t negative k. Well, this guy is in I, so therefore the whole thing is in I. Right? On the other hand, this is bracket of x and y plus k, and then trace x, y, c. Okay. So, right. So this is some element of SL2, and this is something which does not belong to an element of SL2. So actually, my x and y is either 0 or e, or it's either 0 or h, right? Because, yes, it's either commutator of e and f or commutator of h and h, right? So therefore, these are two linearly independent. So c and the commutator of x, y are two linearly independent vectors. On one hand. On the other hand, since it's either h or 0, and this is c, this whole thing belongs to h. Very well. But it belongs to I and belongs to h. So c belongs to h. And this is either h or 0. Yeah, so it is an intersection of I and h. Sorry, I should try it like this. Yeah? So since it's an intersection of I and h, this is 0. Okay, where should I go? I think I should go upstairs. Right, so we know that x, y plus k trace of x, y, c is 0. Then it means that actually this 0 and this 0. So actually we know that x, y equals 0 and k trace of x, y equals 0. So since this equals to 0, okay,
So isn't it already contradiction since if x equal e or f, it should be h, and h is not 0. If x is h, then we can take y to be something like e. Or can't we?
Sorry. So since this is true, then x equals to y equals to h. But since this is then trace of xy is not so it is not 0 in any case, right? So this is not 0. So first of all, it's like that, but from here we know that k equals to 0, right? Since trace of this is not 0. But since k is 0,
Ну, то есть мы след, то, что след и нулевой, знаем как бы прямым вычислением, правильно?
ну да. Да, а то, что, значит, то, что k равняется нулю, это значит, что x на самом деле принадлежит в i. Поэтому x не может быть h. Все, contradiction. Okay, so it means that there is no non-zero ideal SL2 hat such that it intersects trivially with H. So we proved the theorem. We proved that SL2 hat is Kac-Moody Lie algebra corresponding to this A. Okay, I can go ahead and do something, some more computations. For example, we can understand what is while group. And a fine while group, it's actually just usual while group, semi-direct product with translations. Yeah, so we can see this if we have time, or we can.
7 minutes.
Yeah, okay. I think we can do this. Yeah. Also, you can check which roots are imaginary and which are real here. So delta and all k deltas are imaginary, and alpha 1 plus k, or negative alpha 1 plus k delta, they are all real. Because you can compute the form. So the form is positive for real roots and negative for all imaginary roots. So it's also an easy computation. Okay, let's consider what's the while group. Okay.
Просто когда это куда относится?
У нас вот есть корни, да?
Мгм.
А простые корни? А простые корни?
Ну, простые корни — это альфа 0 и альфа 1. У нас их всегда на один больше в афинном случае. То есть у нас есть корни, которые с простой алгебры Ли лезут, и еще один дополнительный, альфа 0 вот в этом случае. Вот.
А у нас вот там корень альфа 1 плюс k дельта и дельта.
Мгм.
А где альфа 0?
А дельта — это альфа 0 плюс альфа 1.
Вот эти два H0 и H1,
Да.
мы умеем на них вычислять все вон те корни, да?
Да. Ну и на D тоже умеем. Вообще на чем угодно умеем.
Значит, умеем отражать.
Отражать умеем, да. Нет, ну, отражать-то мы умеем, но тут и форма есть. Потому что это уже это симметричная матрица. Вот, можно задать форму.
Но она не вырожденная, она вырожденная.
Она будет на h со звездочкой. Нет, я извиняюсь, она где будет?
У нас матрица А, она вырождена.
Матрица А-то вырождена, да. Но нет, ну это не значит, что форма вырождена будет. Нет, форма не вырождена будет. Нет, почему? Почему? На D... Не, она не вырождена. Нет, так она и строится. Собственно, на алгебрах Касса-Муди есть невырожденная форма. Вот. И она как бы на простых корнях задается вот с помощью вот этой симметричной матрицы, которая у нас только здесь и есть симметричная, а потом как бы по градуировке ее как-то надо разнести на всю алгебру Касса-Муди. Ну, то, что А вырожден, это не проблема, потому что это просто значит, что какие-то вектора там между ними есть линейная зависимость. Нет, а в чем проблема?
Что мы вообще обсуждаем?
Ну, сейчас мы обсуждаем, что там есть форма. Вот. И вроде бы почему, как вырожденность формы соотносится с вырожденностью матрицы.
Ну, вообще не совсем, потому что у нас все-таки матрица 2 на 2, а форма на трехмерном пространстве 3 на 3 должна быть.
Ну да.
Нет, у нас мы как пятая задача определяли пространство в определенном списке с птичкой. Вот это. То есть на двумерном.
Нет, ну вот. Define form on H star.
Ну, а нужно двумерное.
Там star действительно, да.
Ну хорошо, ладно, может, нет, сейчас. Да. Может быть. Сейчас, нет, я все-таки хочу, чтобы она. Ну, может быть, она сейчас, если она вырождена на H со звездой. Я вот хочу сказать, что альфа 0, альфа 1 это А 1, 0. Да, то есть что? Минус 2, да. Альфа 0 плюс альфа 1. Вы говорите, что это сейчас лежит в ядре. С альфа 0 это 2 минус 2 и альфа 1, да. Да, она действительно вырождена на альфах. Ну да, не, вырождена, да. Нет, ну, видимо, я ошибся чуть-чуть. Нет, как построить невырожденную форму как бы на алгебре Касса-Муди? Ну, видимо, не совсем так. Вот. Ну, хорошо, я в деталях как бы не помню, как это. Вот, нет, я хочу другое. Значит, давайте возьмем и посмотрим. Значит, у меня есть, let's introduce the following element, lambda 0. It's an element in H star. So it's on C, it's 1, on H, it's 0, and on D, it's 0. So I would like to see how SI So the question is how Si I01 acts on H star. Well, actually HR star. So this is span pi span whatever span of maybe of real of the following things: alpha 1, delta, and lambda 0. Okay, so these are some computations. Well, for example, I can compute S1 on lambda 0. It is lambda 0 minus lambda 0 of H alpha 1. Alpha 1. So this is, lambda 0 of H is 0. So this is just lambda 0. And S0 of lambda 0, this is lambda 0 minus lambda 0 of C minus H alpha 0. So this is lambda 0 minus alpha 0. But I would like to see it in this basis how it looks like. So this is actually alpha 1 minus delta. Delta is alpha 0 plus alpha 1 plus lambda 0. Also, you can check that Si of delta is just delta for each I. And yes. And what about Si? So I have S1 of alpha 1 is of course negative alpha 1. And what is S0 of alpha 1? Okay, it's some computation, which is very easy, actually. So alpha 1 minus alpha 1 of H0, alpha 0, right? So it's alpha 1 plus 2 alpha 0. So it's negative alpha 1 plus 2 delta. So now we know everything. We know how S1 and 0 acts on these three vectors. And so what I would like to see from these computations is that certain affine space inside this is invariant with respect to the action of S1 and S0. So actually let me consider so C alpha 1 plus C delta plus lambda 0. So this is an affine space, right, two-dimensional. And it is invariant with respect to action of S1 and S0. With respect to W0. Well, we just can, check that S0 acting on lambda alpha 1 plus mu delta plus lambda 0. It's negative. Yes, I mean, you can like just compute. So let me just give you the answer. So like this, plus some other delta plus lambda 0. So what I need is this part. And S1 acting on lambda alpha 1 plus mu delta plus lambda 0, it is, well, it's just negative lambda alpha 1 plus mu delta plus lambda 0. And also it leaves, I can quotient by delta now, right? Because S1 and S0 does not leave delta invariant. Right, so I can take this thing, I don't know, let's denote it somehow, V alpha delta. So I can consider action of V alpha delta by quotient by C delta. Right, so W acts in here actually. But this is, identifies naturally with just maybe not even C, but since we had real span, maybe R delta. So this is identified naturally with R, something spanned by alpha 1, right? And how W acts if under this identification, it just acts like this. S1 acting on lambda alpha 1 is just negative lambda alpha 1. I consider only real span. I never go outside, so I can consider. Yeah, so here is again. And S0 acts as follows. It just reflects, but then adds alpha 1. So I can consider, instead of these generators of W, I can consider two other generators. So take the following generators of W. I take S1, and instead of S0, I take T alpha, which is, now I need correct order, it's S0, S1. And if you check, then T alpha acts as a translation. So I take some general vector. It just takes this vector and translates it by alpha 1. Like adds alpha 1. So you have reflection as 1 respect to the origin. And you have now translation by vector alpha 1. And so actually your while group, well, it's generated by these two things, and it acts on this affine space, like on this quotient, as reflections and translations, but also this action is faithful. This one is a bit technical to check. It just can write every element in your while group is S0, S1, S0, S1, or S1, S0, S1, S0, some number of times. And you can see that you can just uniquely write it as some power, as S1 to the power 0, 1, times T to some power. And you can write it uniquely. And none of these elements will go to 0 under this action. So this action is, so maybe claim that I will leave it like that since I don't have much time. That action of W on, so claim on this is faithful. And from this, you can actually make a conclusion that W is S2 and then semi-direct product Z. So this is why it's a affine while group. So it's a usual affine group of SL2, semi-direct product with translations on alphas.
Кто из них нормально такой?
Нормальная Z, на которую действует. Нормальная же, на которую действует, правильно? Должна быть.
Ну да, который вкладывается. Я как-то Z сложен. Ну, достаточно.
Все, что порождено Т альфой. Ну, если я сопрягу S1,
Возьмем альфа минус 1, например. Ой, лямбда.
если я сопрягу S1, то я получу Т альфа в минус 1.
Да, а насчет того, что Т альфа к лямбда минус 1, он же переводит его в 0, да?
Т альфа переводит кого в 0?
Минус альфа 1.
Ну, правильно, да, потому что он прибавляет просто альфа 1. Да.
А 0 не переводится. Ну да, окей.
Ну, понятно, что если вы захотите прибавить альфа 1, а потом отразить, это все равно, что вы отразили, но как бы вычли альфа 1, потому что он развернулся. Вот вы подействовали как бы вот этим на это. Вот, все. Спасибо большое. Так, ну как, следующий четверг, те, кто там еще не писал, тогда и по той же схеме, я просто в Телеграме кину задание.
Окей, ну не надо вам писать там на почту.
Нет. Ну и там отдельно, видимо, я создам слоты, да, для задачек. Может, вот здесь.
А осенью будет вот про что-то такое.
Не
будет,
будет.
да? А, не будет?
Он отменился, да.
Что?
Курс афинной алгебрикации мутих не будет.
Жаль. А чего, они приезжают?
Борис Ильич Фейгин, он уволился недавно.
Что он?
Уволился. Просто.
Видишь, да? По-моему, Рыбников сколько?
Ну, планировалось, да, вот это. Нет, он...
Не, кстати, Рыбников не уволился.
А Рыбников не уволился?
По-моему, он еще держится. Ну, в смысле, из лаборатории-то он уволился. Ой, надо это выключить надо. Ну, в смысле, из лаборатории-то он уволился. Ой, надо это выключить надо.